I'll present you a little bit of the development we had like this year on this project hosted in the Environmental Geoscience program. It's basically, the title is long because I guess it described kind of like two activities within the title. One is the first part, which is the one I will talk about, which is really developing doing the research and development to develop the actual tools of clumped isotope measurements on dolomite. And then the second part is the application of that on an actual case, which will come hopefully this year. We got the sample now. But first of all, I just want to acknowledge right off the bat the team that is working there, and especially Benjamin Fozu, which is is a postdoctoral research scientist at the GSC and the Delta Lab in Quebec, and he has done quite a bit of work on this activity. And then we have our collaborator at University of Ottawa, Tom Hall and Ian Clark, and our funding partner, Nuclear Waste Management Organization. So a bit of context, Nuclear Waste Management Organization has been tasked to evaluate and try to find potential sites to implement a deep geological repository for storage of Canadian nuclear waste. And so several sites have been investigated, crystalline sites, sedimentary rocks as well. And one of the site lies in the Michigan Basin. And it is important for a deep geological repository to evaluate how stable the actual rock was chemically and physically over a geological timescale, because the idea is to isolate those waste from the surface over a very long timescale that we're not used to as human beings. So this is why a lot of characterization, geoscientific characterization, have been done on several sites, and one site in particular on the eastern flank of the Michigan Basin has seen like probably more than 15 years now of geoscientific characterization. And I'm gonna dumb it down really and simplify like what came out of all those work, and it's way more complex than that and way more complete than that. But mainly two systems have been characterized like in the Ordovician part of the sedimentary succession, with an extremely tight aquiclude confined for at least 216 million years, and a lower system that is just overlying like the Precambrian, and that is a bit more complex, was like a more complex paleofluid history. And the picture you can see on the left is a picture coming out of a paper of one of our colleagues at the GSC Ottawa, Dwayne Petz, where he actually measured quite a bit of different temperature and fluid inclusions, or derived temperature from fluid inclusion from this lower part of this system. And to us, this is what we're going to target, because it's really of interest to benchmark a new geothermometer, which is what we're trying to do with this clumped isotope on dolomite, is to evaluate how that can be used as a geothermometer. So benchmarking it with existing temperature is really interesting for us. So I'm talking about clumped isotope. I'm just going to explain quickly what it is. Some of you are familiar with isotope geochemistry, where we measure the abundance of heavy isotope relative to standard. And here, what we're doing, instead of measuring the abundance of heavy isotope alone in a material, we're actually looking at the abundance of two heavy isotope bonded together in this material in a molecule. So we call this molecule multiply substituted isotopolog. And what we're doing at the GSC in Quebec at the Delta Lab is that we're applying those clumped isotope on carbonates. So we're actually looking at the abundance of bonds between C13 and O18 in the crystal lattice of carbonate. And so those clumped species are really, really low abundance in the nature. So it's very complicated to measure them. And we need to go through extensive preparation of the carbonate. We need to acidify the carbonate and make a CO2 from the carbonate and purify it to a very, very purified state, and then inject the CO2 in a very sensitive mass spectrometer here in order to be able to measure those subtle differences of mass. So why are we going into all this hassle? It's because actually the lower the crystallization temperature of a carbonate, the more you're going to have of those clumping of heavy isotope in a crystal lattice. And the higher the temperature of crystallization, the less clumping you'll have. So that makes actually a single phase geothermometer, and we can use it as a geothermometer because it's really predictable, the behavior of clumping versus temperature of formation is really predictable, and we can calibrate it. So we now can do this on calcite very well at the geological at Delta Lab. It's a pretty soft carbonate. It's easy to acidify. We can acidify at 70 degrees Celsius. It works very well, and we can apply it to several environmental and to several natural systems. Now, what we need to do is to switch to dolomite in order to be able to compare what we can get in terms of temperature between dolomite and calcite that are co-located in natural sample, and understand a little bit what's going on there. So that's what we were trying to do here over the year. And we started by modifying heavily the keel-foil carbonate device, so this sort of washer and dryer you saw on the previous slide, in order to increase the temperature of acidification of the carbonate and apply it to dolomite. Then Ben got quite an expertise in cooking synthetic dolomite in the lab at different temperature in order to produce anchors to calibrate the thermometer. And then he calibrated the clumped isotope thermometer for dolomite. So I'll show you that. So this washer and dryer kind of like thing you saw is called a keel 4, and we modified it, so we rebaptized it Frankenkeel. Basically, all the modification we've made are like plumbing modification, remachine some pieces and stuff like that. And that allow us to go from an acid digestion temperature of those carbonate from 70 to 90 degrees Celsius. Actually, we could go higher. We can go to up to 120, but we have tested it up to 90 right now. And that the consequence of that is that we can decrease the reaction time down to 10 minutes, so high sample throughput, but also, which is very important, what we want to do is attack like more resistant minerals, such as dolomite in our case here, but we are planning on doing siderite that could be very interesting for other systems. So that's just a close-up of the interior of the oven. So the top of the washer dryer, you'll see here like an acid bulb, like with acid capillary that go down to acid valve and little vials down there where the carbonate is. What is one of the interesting part here that we've changed is the acid capillary. They're now made of a special alloy that is actually the same alloy that we're using on the Apollo mission. So very heat resistant and very corrosion resistant. So it's really has run for more than 6 months now without any failures. So we have a very unique instrument right now that is opening up a lot of application, even in potentially in hydrothermal mesothermal system for ore mineral deposit, for example. So now Ben has done quite a prolific work in cooking dolomite. And basically what he does is he mixes equimolar solution of salts to bring like calcium, magnesium, and carbonate together, bicarbonate together in order to produce an amorphous gel that is kind of a high mag carbonate sort of thing that he heats after that at the target temperature for weeks. And that allows to crystallize some mineral that we check at the GSC Ottawa in the mineralogy lab with X-ray diffraction. And we realized that we were getting actually weakly to moderately ordered dolomite, which is great. It's not quite dolomite, it's proto-dolomite. We don't have the crystallographic ordering that would be necessary for calling it a proper dolomite. But it doesn't matter because the isotopic bond ordering is not influenced by the crystallographic ordering, and we can use them as calibration material. For the very high temperature anchors, we are actually taking advantage of a phenomena that happens on the clumped isotope distribution in a carbonate crystal. When you heat them above a certain temperature, you start to diffuse apart the heavy isotope one from each other and like breaking those clumps of heavy isotope. And if you heat it for a long period of time enough and at high temperature, you will actually go to a stochastic distribution, so a totally random distribution of your heavy isotope in a crystal lattice. And that creates you like a very high temperature anchor. Problem when you want to do that, if you heat it to 1,000 degrees Celsius, which is what is necessary, you're going to actually just disintegrate your carbonate. You're going to decarbonate it. So you need to have a very high confining pressure. We don't have this at the GSC, so we paired with very nice folks at the University of Western Ontario. Those are people that do very routinely experimental petrography, so that we're able to press and heat our carbonate to 2 gigapascal and 1100 degrees Celsius to 4 hours. Then we quench it down. We check the mineralogy again with XRD. We're lucky, it's dolomite, we're happy. And then we measure the CAP 47, which is the clumped isotopic abundance. So that's the state of the dolomite calibration at the Delta Lab now. And you see in the y-axis, that's the abundance of clumped isotope. On the x-axis, it's the inverse function of temperature. And we have a nice mathematical relationship, which tells you that if you can measure this, which we can now, we're able to back calculate the temperature of precipitation. So we're spanning now actually below 40 degrees Celsius at the low end of the thermometer up to 1,100 degrees Celsius. So we're ready to jump into the Michigan Basin now, and stay tuned. This is going to come this year. We have the sample now, and we're going to microdrill several little veins and vugs in order to have a little bit of material. And our goal here is to sample dolomite and calcite phase that coexist, to get additional information on the temperature history of the sedimentary package, and also provide information when no other geothermometer are present, like when we don't have fluid inclusion, for example. Then one of the things that I would like to check as well is when you have like a fluid that goes into a vein like that with a temperature that is higher than the host matrix, would this temperature actually alter the isotopic bond ordering of the matrix, the calcite matrix around? So we're probably going to try to get transect around a vein in order to explore those fundamental questions. So with that, I'm done. And if you have any question, feel free to ask them now or later.